Hi, everyone. I want to talk you through problem number 79. So we have an airline pilot. He falls from a height of 370 meters to the ground, zero height, and he does so without his parachute opening. He lands in a snowbank, which I've illustrated here in red, and then he creates, during that fall, his deceleration in the snow. He falls for 1.1 more meters and forms a crater 1.1 meters deep, C. So assuming that the pilot's mass is 88 kilograms, and that his initial impact speed is 45 meters per second, then we want to estimate the following. The work done by the snow in bringing him to rest. Then we want to know what the average force exerted on him by the snow was to stop him. And then we want to know the work done by the air resistance as he fell. And throughout, we're going to model him as a particle. So just as trying to build a little bit of intuition, we are falling 370 meters. Now, 370 meters, if you're falling in just gravity, is quite an experience. You're going to fall very quickly. So 45 meters per second being reached at the bottom tells you that there's another force involved. Generally, that the gravitation that we're used to here at Earth is counteracted by, for instance, air resistance, the force of the air or the acceleration that he experiences due to air resistance. All right, and then these are going to counteract one another. So the work done by the snow bringing him to rest. How are we going to achieve this problem? All right, so the first thing that we need to apply is the work energy theorem, which says that any change in energy of an object is due to work being done by that object. And so for us today, we'll just be considering the change in the kinetic energy, which, by the way, is the same as the change in the potential energy in this case. But this change in kinetic energy is going to be entirely due to the snow slowing him down from 45 meters per second to 0 meters per second here at the bottom. And so all we're going to do is just have our kinetic energy equation, 1/2 mv final squared minus v0 squared. And because our initial velocity, v0, is 0, then we know that all of the kinetic energy will have to be taken away. And so that means that we just go through our calculation, we plug in things to our calculator, 1/2 of 88 kilograms times 45 meters per second squared. So looking at units, this is a kilogram here, and then 45 meters per second becomes meters squared per second squared. And what that means is that we have a kilogram, meter per second squared. And so a kilogram meter per second squared is a Newton, and we have one more meter left over, so that means it's a Newton meter. And we define this as a joule, which is the unit of energy, and it's also the unit of work. So if we plug this into our calculator here, we get roughly 9 times 10 to the 4 joules if you go through the whole thing. All right. Now let's talk about part B, the average force exerted on him by the snow to stop him. We need to estimate that. So work we generally can think of as a force being applied to an object over a certain distance or displacement. And what that means is that if you actually were to go through and look at all of the different density layers of the snow, and you were to quantify how much he fell through each little density layer, you would get the total work done by the snow. But you can also estimate this by just taking an average. We don't know necessarily whether the snow has a particular density or not at different layers of the snow, but we can model it as an average force being exerted over the full fall into the crater. And so this average force of the snow over the crater distance is equal to the work done by the snow. All we have to do is invert this algebraically. So the work done by the snow over that crater distance is just the average force. And we can compute that given what we know about the work of the snow from the previous problem, and then divide by the crater distance, which means that we've had the snow exert roughly 8 times 10 to the 4 newtons of force on average over the full 1.1 meters. Okay? Now we need to find what the work done on him by the air resistance was as he fell. So we want to figure out a few things. Remember that gravity acts everywhere. It doesn't matter if there's air around, it can just be in vacuum. And so what we want to find conceptually is the difference in his final velocity in the air versus his final velocity without the air. In other words, this is a statement that says we know that the kinetic energy that he would achieve in the vacuum is different. It's not equivalent to the one that he achieves in the air. So this final velocity here is just going to be different. We expect that the final velocity in vacuum would be much higher than 45 meters per second. So we know what the acceleration of gravity is in vacuum. We know that he starts with with initial velocity of 0, and then he'll achieve some final velocity over some period of time to achieve a full gravitational acceleration. We know this acceleration equation, and we can invert it to find the time of his fall. Now, this doesn't help us just yet because we don't know what the final velocity of him in vacuum is, but we can figure that out with the application of kinematic equations. So what we can do is we can take this time and we can plug it into our main kinematic equation, which says that any displacement or any distance traveled h for us, the height fallen, would be equal to any initial velocity times the time of that fall plus 1/2 times the acceleration of that fall, g, times t squared. Because we know that he doesn't start with any velocity, this goes to 0, and so we have just 1/2 gt squared left. However, we know what the time he would be falling in vacuum is. It depends on his final velocity in the vacuum divided by the gravitational constant acceleration, sorry. And so we can plug T vac in here as VF vac over G, and we can square it. We know that there's going to be 2 G's here. One of them is going to cancel. One of them is going to be left over. And then algebraically, you would get G to the first power and 2 in the denominator, where V final vacuum is in the numerator. Now you can invert that algebraically. What you can find is that the final velocity in vacuum is the square root of 2gh. And this is a really good formula for everyone to remember because it tells you the effect of acceleration g over a particular distance h. And as long as there are no external forces like air resistance acting on a body as it falls, this is what it's going to be. And it actually doesn't have to be falling. It can be linear acceleration horizontally, where g would just be a different acceleration and h would be a distance in the x direction, for instance. So this is a really important formula to remember. So all we have to do is just plug this in. So we have 2 times 9.81 meters per second times 370 meters of fall. And you'll get that he should have achieved in vacuum roughly 85 meters per second. So that means that 85 meters per second, as we said, is a lot different than 45 meters per second. So the kinetic energy is different. And what that means is that he has had, if you will, a change in energy, a change in kinetic energy. He's lost something to the air. And so the change in that kinetic energy is equal to the work that was done by the air. It was a force exerted over a distance of that fall. And so you can take the kinetic energy that he would expect in the vacuum and subtract it from what he actually achieved in the air, and you can get the following, which is where you have 85 meters per second, and you're going to square that and then multiply by 88, of course subtract 45, and you're going to get 2.3 times 10 to the 5th joules. So that's the problem. Hope you guys enjoyed it. Let me know if you have any questions. Thank you.